Good morning. Sorry, I'm just trying to get this set up really quick. Good morning. Good morning. All right, and that's the end of the class. Good morning. We're sponsored by Clear today, folks. It's just one of those days. No blue, no orange. Just Clear. All right. So, we're going to talk about, over the next, like today, tomorrow, probably, we're going to talk about Taylor and Maclaurin polynomials. And technically, we're not, we don't need to talk about Maclaurin polynomials or Maclaurin series, but well, you guys will see why once we actually get more into the definitions of what these things are, but it's not really much different to talk about a Maclaurin polynomial compared to a Taylor polynomial, so we'll go ahead and at least mention it. But I believe that was one of the things that was listed as not being on the topics list for the AP test. Double check that. I guess it still could be in there. We'll see. But so, some kind of general information. The whole point of these polynomials is we are going to use these to approximate values, right? Kind of in the same sense that we have used we use linear approximations in AB. This is kind of that same idea, but we're just expanding it. We're going to make it potentially better approximations. All right, and here's a couple key notes that we'll see help us as we do some examples. If the value of the function and the polynomial are the same, that's good for us. If the value of the first derivative and the polynomial are the same, that's even better. And more derivatives are the same, the better the approximation. So again, what does any of that mean? Well, we'll see it actually in the examples, and I'll point it out as we get to it. But we're using this to try to approximate the values of a polynomial, right? That's our goal. So this is a Taylor polynomial. So if f of x has n derivatives at c, then, okay, and we'll denote this with this p sub n of x. All right, so this is called the nth degree Taylor polynomial. So yes, this will be something that you need to memorize. But it's not really, you just need to make sure you have this part down. right? Because after that, it's really just like plugging in a number, right? So this term right here is just if you plug in n equals 1. This term is just, or this whole term is just if you take that thing I circled and then plug in 2, right, etc., and then plug in 3, plug in 4, however many we need, however many the question asks for. Okay, but as long as you memorize, really it's just memorizing this first piece, or not first piece, but this thing that I circled, right? Why is it written as 2 factorial specifically? Yeah, it is just 2, but it's just showing you that that's the pattern. So 2 factorial, but the next term it would be divided by 3 factorial, which is, actually 6. So it's just showing it's just showing the relationship that in this term, all of these things are 2, right? Because that's what the formula says is and all of these things are the same value. So for this term, they're all 2. But for this term, for that term, they're all 1. So it's just showing the pattern. But yeah, you're right. 2 factorial is just 2. So we start with just the value of the function, f of c, and then we add on this now new formula for each term. Okay, and we'll be asked different degrees. So maybe it says find the 2nd degree polynomial, find the 5th degree polynomial, find the 132nd degree polynomial. And that'll tell us how many of these numbers do we actually need to plug in and how many of these terms do we need to calculate. Okay, so an illustration of what does a Taylor polynomial actually do. So let's see. Let me pull up this link. Very wavy. Okay. So let's say that this red curve is the actual function, right? That's our f of x. Right, and now we are wanting to use a Taylor polynomial to approximate it. Okay. So as we plug in larger values, right? So if I plug in 0, right now the approximation is this blue line. Okay. Not very exciting, right? And not a very good approximation. It's a good approximation for, that one spot where it matches up, but other than that, not so great. Okay, so that would be the 0th degree Taylor polynomial, right? Just that. But now let's bump it up to 1. So we add another term. Okay, so now you can see it looks a little better. Right, it kind of now fits in a larger range. All right, so now let's bump it up to the 2nd degree. Okay. And 3rd degree. All right, looks even better. 4th degree. 5th degree. 6th degree. 7th degree. Okay, so we can see that every time I add another term of a Taylor polynomial, my approximation gets better and better and for a longer period of time. Okay. Because initially, this polynomial is good for approximating values that are right around 1.5 or whatever. But if I have even like a 6-degree polynomial, okay, now this is really good for approximating for quite a while, maybe from like -1 to +4 is like, these are all really, really good approximations, if not perfect, right? Or 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, okay, etc. And it will just continue like that forever, that each term that I add on will make my approximation better for longer, right? For a wider domain, I guess. All right, so that's what these Taylor polynomials do, which is pretty neat. Just by adding on one term, my polynomial now gets much better in how it approximates the function, whatever it is. Infinite Taylor polynomials, yes, exactly. And so if we took that series where we added on infinite number of terms, then we would just get the same function, right? And we'll talk more about that too. Okay. So use a 3rd-degree Taylor polynomial centered around 0 to approximate f of x. All right, let me shift this down so it's a little easier to see. Okay, so 3rd degree. So a Taylor series or a Taylor polynomial always starts off with just the actual function, right? Oh shoot, let me bring up. Where'd my other screen go? Sorry, this has kind of been bugging out on me today. As per usual. Okay. So this will just start with plugging in 0, right? Because that's what this first term always is, right? It's just the value of the function at whatever we are centering it around, right? So that's what that C represents, is where are we centering this polynomial, right? Where do we want it to start approximating really well? Okay, and then we go through, and now we start using our formula, our equation. So that's f prime of C, right, over 1 factorial. So this would be times x minus c, but in this case c is 0 because we're centering around 0, so just times x. Plus, so now we move up to the second, so we are now plugging in 2 to that little formula part. So f double prime of 0 times x squared over 2 factorial. Plus, now we want 3rd degree, so we're going to go all the way up to 3 here. So f triple prime of 0 x cubed over 3 factorial. right, so we can see the pattern. First term is just the value of the function of around where it's centered, 0. Okay, the next term, now we're using f prime of x to the first over 1 factorial f to the double prime of 0 times x squared divided by 2 factorial, and then same thing but with 3 in the third term, or that fourth term. But let's actually figure out what these values are. Right, f to the 0, or sorry, f of 0, so e to the 0th power is just 1. Okay, plus, I'm going to do some work down here off to the side. F prime of x would just be e to the x. So f prime of 0 is still just 1. So 1 times x over 1 factorial, so that's just 1 plus x. And then f double prime of x, well, that derivative is still e to the x. So f double prime of 0 is still just 1. That's making my life a lot easier. So this is where we're talking about if those derivatives are just the same, makes things a lot better for me. So f double prime of 0 is 1. X squared is x squared divided by 2 factorial, which is 2. And then lastly, again, I probably just know this, but I'm going to write it out just to show explicitly what we're doing. So the third derivative is again e to the x. So f triple prime of 0 is still just 1. So we have 1 times x cubed divided by 3 factorial. 3 times 2 times 1 is 6. So this is the third degree Taylor polynomial. Centered around 0. Right, because actually when I look at each of these x terms, I'm actually imagining each of those is x minus 0. Right, but x minus 0 is just x, or x minus 0 squared I can just write as x squared, or x minus 0 to the third power I can just write as x cubed. But if it were centered around some other number, then it would look a little different. Now, so what is this actually, again, what is this actually doing? It's approximating. Okay, let me pull up Desmos again. Okay, so here is e to the x. Now let's look at the Taylor polynomial. Now let's build it one at a time. So the very first term of the polynomial was just 1, right? So if I look at this and I just have y equals 1, okay, well, that's not a very great approximation. You know, I get it's something, but it would only be a good approximation right around here, because as I get further away from that, then those two lines are very different. Okay, so now let's make it a little better. So let's add our next term. So our next term was x, so 1 plus x. And okay, gets a little better. Right, so now let's get rid of that blue. Okay, so this approximation is at least sort of increasing in the same way that e to the x is. So it gets a little better. Now let's add on my next term. So 1 plus x plus x squared over 2. Okay. So again, now I have some curvature here. Follows it a little more closely for a little longer, and also starts to kind of curve towards it as I go up as well. So let me fade out this green line now. Okay, so now I have a slightly better approximation. And then our last term that we did, so we have our same stuff from before, but let's add on our very last term that we did, which is x cubed over 6. Okay, so again, it starts to get slightly better in my approximation. It's following it closer for longer. Now, eventually, it still does, separate and become very different, but it's closer than it was before, right? So here was our progression. Y equals 1. Okay, not great. A 0th degree Taylor polynomial. All right, 1st degree Taylor polynomial. A little bit better. 2nd degree Taylor polynomial. A little bit better than that. 3rd degree Taylor polynomial. A little bit better than that. All right, and we could just keep going. Okay. But if I'm just trying to approximate something that is pretty close to the origin there, then it might not be so bad to use this Taylor polynomial. So that's what we're doing. For every term that we add on, the better our approximation gets. Right. So let's use our same Taylor polynomial. So I'm just writing this from the last page. Right, that's exactly what we had as our last answer. So now I want to use this to approximate e to the power of 0.2. Well, that would be approximately if I took my third degree Taylor polynomial and plugged in 0.2. So 1 plus 0.2 plus 0.2 squared over 2 plus 0.2 cubed over 6. So all I did was take my Taylor polynomial, plugged in 0.2, because that's the thing I'm trying to approximate. Okay, well, I think this is something now. Maybe. Works. Okay. Cool. I don't know. That was kind of a process. Also, good morning. Welcome. Don't be surprised if this breaks on me again, because I don't know. It's being really weird, but it's at least working for the next 38 seconds probably. So we'll stick with that. Okay. Whoa. That's fun. Whoa. All right. Whatever. We're approximating. We use that third degree Taylor polynomial to approximate e to the 0.2. Now, if I went this won't right. If I say wanted to approximate e to the 6 to the power of 6.3, third degree Taylor polynomial probably wouldn't be good enough because this polynomial that we used was centered around 0. And so 6.3 is, not super close to 0. Well, it depends on your, relatively, but 6.3 not quite close to 0, especially if we're talking about only using a third degree. Now, if I were using like a 12th degree Taylor polynomial, then yeah, the further out from 0 I get, the better the approximation is still going to be. But for just a third degree polynomial to go that far away from where I'm centered around, it's probably not going to be a great approximation. Can we have Max teach again? Reese seems excited. Okay. Yeah, maybe we'll bring back Max sometime. Okay, so the next piece is a Maclaurin polynomial. Now, a Maclaurin polynomial is the exact same thing as a Taylor polynomial. Okay, the only difference is Maclaurin polynomials are specifically centered at 0. That's it. All right, this is just like earlier in the semester when we were doing the mean value theorem. And then we had Rolle's theorem, which Rolle's theorem is literally just the same thing as the mean value theorem, but if the derivative is 0. It's kind of the same thing we're doing here. Maclaurin really went all out and found the Taylor polynomial, and he's like, well, what about if you center it around 0? Maybe we should call that like a Maclaurin polynomial. Like, that'd be cool. And everyone was fully on board. They loved it. They was like cheering. They're like, yeah, Maclaurin, how did you do it? Taylor sucks. That guy was dumb. He would have never guessed to put it around 0, but Maclaurin did. So thank God we have him. Well, had him in like the 1700s or something. But really groundbreaking stuff from Maclaurin to center the Taylor polynomial around 0. Yeah, but otherwise, same exact thing. Hashtag never forget. Exactly. Right. My personal hero, Maclaurin. I think he was Scottish. Maybe. Okay, so what we just did for this one right? We called this the third degree Taylor polynomial. Now that's correct, but technically, since this is centered around 0, this is technically a third degree Maclaurin polynomial. Maclaurin is the type of guy to trace art and say it's his. Okay. So let's find a fifth degree Maclaurin polynomial to approximate f of x equals sine of x, then use it to approximate sine of pi over 12. Okay, great. So I like kind of just first writing out the actual polynomial, kind of using just the formula before I start actually plugging in the specific things and doing the derivatives. So the fifth degree. Right. Remember, this is centered, it's a Maclaurin polynomial. So it's centered around 0. So my first term is just f of 0. right, plus f prime of 0 divided by 1 factorial, right, times x. And then plus f double prime of 0 divided by 2 factorial times x squared, plus f triple prime of 0 times x cubed divided by 3 factorial, plus the fourth derivative of f of 0 divided by 4 factorial times x to the fourth. Can't fit that last term there. The fifth derivative of f of 0 divided by 5 factorial is x to the fifth. All right, now notice once we get above triple prime, and even you could do this for triple prime, but instead of writing 4 like tick marks to mean fourth derivative, then we just put the 4 up there in parentheses, or we just put the 5 up there in parentheses, so you don't have to list like just a ton of little tick marks. Okay, so now let's actually figure out what these things are, right? So mostly I just need the derivatives. Right, I need the first, second, third, fourth, fifth derivative, and I need to plug in 0 to those and see what I get. Right. Well, so firstly, f of 0. Right, so sine of 0 I know is 1. So I have that off the bat. Great. Now f prime of x, so the derivative of sine, cosine. F double prime, derivative of cosine, negative sine. F triple prime, negative cosine of x. The fourth derivative, positive sine of x. And the fifth derivative, cosine of x. Right, so those are just the derivatives themselves. But as we look back up at our polynomial, we want to know, okay, now take these derivatives and plug in 0 because it's centered around 0. Great, so let's plug in 0. So cosine of 0 is 1. Negative sine of 0. So, oops. 0. The third derivative of 0. So negative cosine of 0. So that's negative 1. Sine of 0, 0 again. Cosine of 0, 1. All right, so I kind of have this cyclical nature that we can see going 1, 0, negative 1, 0, 1. All right, so now I just need to put this all together. I don't know that I have room up there. So I'm basically going to write that same purple polynomial that I had up here, except I'm actually going to plug in those derivatives now that I solved for. So f of 0, the first term we decided was 1. Okay, plus 1 over 1 factorial times x plus 0 over 2 factorial times x squared plus negative 1 over 3 factorial times x cubed plus 0 over 4 factorial times x to the 4th plus 1 over 5 factorial times x to the 5th. And we can see that we should be able to simplify this a bit because that's just 0 since I have 0 in the numerator. So times 0 divided by 0, or sorry, times 0, 0, 0 divided by 2, 0. Okay. And then same thing with this one. This term is also just 0. So actually, my polynomial is 1 plus 1 divided by 1 is 1, so just 1 plus x plus negative 1 over 3 factorial. 3 factorial is 6. X cubed. Plus 1 over 5 factorial x to the 5th. 5 factorial, what is it? 120? Wait a minute, this doesn't look right. Oh, come on, guys. Why would you do this? This is not true. Sine of 0 is 0. So that's fine. We just don't have this first term. So it's just these. All right, so this is the 5th degree Taylor polynomial. Now, what is the actual value? Oh no. Drop my pen. Right, because we want to know what is the approximation what is the approximation of sine of pi over 12? So sine over 12 is approximately the 5th degree Taylor polynomial of pi over 12. Right, so that would be pi over 12 minus 1/6 times pi over 12 cubed plus 1/120th times pi over 12 to the 5th. And we could type that in our calculator, and the answer is whatever. But the point is, if whatever we're trying to approximate, we just plug it into our polynomial. Okay, but if I wanted to approximate what is pi over 9, well, then I would just plug in pi over 9 to my 5th degree polynomial. There's no particular reason why we did the 5th degree polynomial on this one other than the problem told us find the 5th degree polynomial. Okay, so it's not like you'll have to choose like, oh, do I do a 4th degree here, a 5th degree here? It's just whatever the problem tells you to do. Okay, but remember, the larger degree Taylor polynomial that we use, the better our approximation is going to be overall. Okay, let's try again. Find the 4th degree Taylor polynomial for y equals natural log of x centered at c equals 1. Then use it to approximate natural log of 1.19. Great. Okay, so centered at 1. So our first, not 0, 1. Well, I'll write it like this. All right, so our very first term in a Taylor polynomial is you just take the function, whatever it is, and plug in wherever it's centered around. So in this case, our function is y. So if I plug in 1, because that's where it's centered. Then we move on to doing that repetition of formula. So f prime of 1, because it's centered around 1, divided by 1 factorial, times x minus 1 to the first, plus second derivative of 1, 2 factorial, x minus 1 squared. And then the third derivative, plug in 0, 3 factorial, x minus 1 cubed. Don't know if this will fit. Divided by 4 factorial, x minus 4 to the fourth. I think that squeezes onto your guys' screen. Okay, so notice, right, in our last two examples, awesome. In our last two examples that we actually made the polynomial, they were centered around 0. But now, since it's centered around 1, that's why it isn't just x or x squared or x cubed or x to the fourth. It's, oh, why did I put a 4 there? All right, it's x minus 1 or x minus 1 quantity squared or quantity of x minus 1 cubed or quantity of x minus 1 to the fourth. It's nice, though, if it's a Maclaurin series and it's centered around 0, because then we just have good old x, x squared, x cubed, x fourth, etc. But otherwise, we should have a binomial to the power of whatever it is. Okay, so now let's just figure out what all of our derivatives and such are. So I'll go down a little bit. All right, the first derivative of natural log is 1 over x. Okay, the second derivative, so depending on how you want to think about it, Remember, this is the same thing as x to the negative first. Okay, so that could help thinking about it for the chain rule. So negative x to the power of negative 2. So the third derivative, 2x to the power of negative 3. And the fourth derivative, negative 6x to the power of negative 4. Now, it actually might be beneficial to go ahead and write these in just like the fraction form as well. Because, remember, we have to take all these derivatives and plug something in. So it's kind of hard. Well, not hard, but it's harder, I think, to think about numbers to a negative power rather than thinking about it like this. But, I mean, either way, the point is we have to go through and we have to now plug in 1. You guys, why am I so bad? I started strong. All right, so we're centered around 1. So 1 is what should be plugged into all of these derivatives. I started strong with the 1s, and then I reverted back to 0s. Sorry. Okay, so we're going to go through each derivative, substitute in 1. I'll use a different color. Okay, 1 over 1 is 1. Great. 1 over 1 squared is 1, so negative 1. The third derivative, so 2 over 1 cubed is 2. And the fourth derivative, negative 6 over 1 to the fourth, it's negative 6. Great. Now we can take these values and plug them in where they need to go in our original polynomial that we wrote. Okay. So y of 1, so my first term, natural log of 1 is 0. That's awesome. Okay, plus 1 over 1 factorial times x minus 1 plus negative 1 over 2 factorial is x minus 1 squared plus positive 2 over 3 factorial times x minus 1 cubed plus, or wait, yes, plus negative 6 over 4 factorial times x minus 1 to the fourth. Okay, but I'm going to do some more simplifying here. So 0, that first term 0, I don't need to write 0. The second term, 1 over 1 factorial, that's just 1. So I'm just going to start by writing x minus 1. Okay, since that numerator is a negative 1, then I'm going to change this just to a minus sign. 2 factorial is still 2, so minus 1/2 x minus 1 squared. Plus 2 divided by 3 factorial. So remember, 3 factorial is 1 times 2 times 3. So that means there's a 2 in the numerator and a 2 in the denominator. So those will cancel. So plus 1/3 x minus 1 cubed. And then for my last term, negative 6 over 4 factorial. Now 4 factorial is 4 times 3 times 2 times 1. Well, wait a minute. Inside of 4 factorial, that means there's a 3 times 2. Well, 3 times 2 is 6. So I have a 6 in the numerator, 6 in the denominator. So this will become minus 1/4 x minus 1 to the 4th. So this is the 4th degree Taylor polynomial for natural log of x centered around 1. Okay, questions on where I know there's a lot going on. Okay, a lot of numbers, a lot of symbols. Questions on where numbers came from. Questions on how I simplified something. So the last part of the question says, use it to approximate natural log of 1.19. So that's why we use Taylor polynomials. So that is approximately our 4th degree polynomial that we found if we plugged in 1.19. So that's x minus 1. So 1.19 minus 1 is 0.19 plus 1/2 times 0.19. Or minus 1/2, sorry. Plus 1/4 0.19 squared. Nope, that's squared and that's cubed. Hold on. I hate scrolling up and down. I get messed up. Squared, cubed. Okay, yes. So squared, cubed, and then minus 16.19 to the 4th. And again, that equals whatever. We could plug that in, calculate it. But whatever it is, it's a pretty good approximation of what is natural log of 1.19. Okay. So I'm gonna leave it off there for today. And then we'll come back tomorrow and do some more practice with Maclaurin and Taylor polynomials and using them to approximate.